Bert.
No! The Standard Deviants present the Supercharged World of Chemistry, Part 2.
Starring Galila Azraz, Gabrielle Smith, Jeremy Clavens, Dina Rubinson, Malcolm Smith, Trevor Dean, Chuck Hinshaw, Christiana Celeste, Tessa Monroe, and Chaz Maston.
Hi, I'm Malcolm Smith, and welcome to the Supercharged World of Chemistry, Part 2. Over the next 2 hours, we will charge you up with tons of information about calorimetry, enthalpy, quantum mechanics, orbital diagrams, Lewis structures, the octet rule, covalent bonds, and much, much more.
These VCRs are amazing machines. If you miss something while you're watching this tape or you just want to see it again, you can always pause the tape, stop the tape, and rewind the tape.
Now it's disclaimer time. To truly absorb the intricacies of chemistry, you must attend your classes, listen to your professors, and study the material.
This is the Supercharged World of Chemistry Part 2. So in this video, we're going to assume you know all the stuff we talked about in the Supercharged World of Chemistry Part 1, like the states and properties of matter, the elements, molecules, and compounds. You should know how to use the periodic table, SI units, and significant figures, and it's essential that you know how to balance equations.
And moles! Make sure you can do calculations with moles and convert from grams to moles. In chemistry, moles are everywhere.
Part 1. Thermochemistry.
Thermochemistry measures the heat changes associated with chemical reactions. In other words, thermochemistry deals with how much energy moves around as a result of a reaction. We measure energy in joules, which is an SI unit of measurement.
Before we launch into the Supercharged World of Chemistry Part 2, let's briefly go over some of the terms and formulas we learned in Part 1. If any of you loose cannons don't think you need to review the stuff in Part 1, just fast forward the tape until you see this graphic of an exploding experiment. Remember, we go over all this stuff in detail in Part 1. So here we go. It's review time.
Chemists study the interactions between energy and matter. Matter is anything that takes up space and has mass. When you think matter, think space and mass.
Energy, like light and heat, does things to matter. Solids, liquids, and gases are all examples of matter.
Each solid, liquid, or gas has a unique set of characteristics, or properties, that we can observe and measure.
There are two kinds of properties, physical and chemical. The physical properties describe physical attributes or physical changes. The chemical properties of matter describe the way the matter acts during chemical reactions. Two types of matter are homogeneous matter and heterogeneous matter. Homogeneous matter has the same physical and chemical properties throughout. Homogeneous matter is also called a substance. Homogeneous mixtures of substances, also called solutions, have the same chemical and physical properties throughout as well. Heterogeneous matter is a mixture of pure substances with different chemical and physical properties.
Elements are the building blocks that by themselves or with other elements make up all matter. An element is a substance that contains only one kind of atom.
You'll find all the elements listed in the periodic table. A substance consisting of two or more elements combined in fixed proportions is a compound. And the single unit of a compound, a chemical combination of two or more atoms, is a molecule.
A chemical equation is a shorthand way to describe a reaction that gives the formulas for all the reactants and the products.
Chemical equations have to be consistent with the law of conservation of mass, which says that atoms aren't created or destroyed in chemical reactions. To avoid breaking the law of conservation of mass, you have to learn to balance equations. Atoms are made up of protons, neutrons, and electrons. Protons, which have a positive charge, and neutrons, which have no charge, reside in the nucleus of the atom. The Wren isn't so bad, and they get to hang together. Electrons, which have a negative charge, orbit the nucleus. We'll talk a lot more about the location of the electrons in the atomic structure section of this video. The total number of protons plus neutrons in an atom's nucleus is the mass number. The number of protons alone in the nucleus is the atomic number. A mole is a unit of measurement that represents 6.022 times 10 to the 23rd atoms, molecules, or small things like that. The magic mole number, 6.022 times 10 to the 23rd, is also known as Avogadro's constant. You can look up the atomic masses of atoms in the periodic table. The table will give you the atomic mass in AMUs, atomic mass units. 1 mole of any type of atom has a mass in grams equal to the atom's atomic mass measured in AMUs. Isn't that dadburn convenient? Molecular weight is the combined mass of the group of atoms forming a single molecule. Add up the masses in AMUs of the atoms forming the molecule, and you have the molecular weight. Formula weight and molecular weight are almost the same thing. But formula weight finds the weight of atomic structures like crystals, which are not molecules. In many chemistry calculations, you have to convert grams to moles. Here's the formula you'll use. Multiply the weight in grams of your sample by 1 mole of the substance you're working with over the weight in grams of 1 mole of your substance. This type of unit conversion is called the unit factor method. Multiplying by 1 mole of the substance over the weight in grams of 1 mole of the substance is just like multiplying by 1, so it changes the units without changing the quantities.
The percent composition of a compound gives the ratio of elements that make up the compound. In other words, it specifies what percentage of the total compound each component element represents.
Here's the formula to find percent composition. Take the number of atoms of one element in the molecule, multiply it by that element's atomic weight. Divide that quantity by the molecular weight of the compound. Then multiply the whole deal by 100. Do this for each of the molecule's component atoms.
To calculate the masses of substances taking part in a chemical reaction, follow these 4 steps.
First, write the balanced equation for the reaction. Next, convert the known mass of one of the reactants or products to moles. Then, use the balanced equation to set up the appropriate conversion factors so you can find the number of moles of the other reactants or products. Finally, convert your values from moles back to grams.
The molarity of a solution is the number of moles of solute in 1 liter of solution. The equation you'll use to find molarity is N, the moles of solute, divided by V, the volume of the solution in liters. You can rearrange the equation using molarity times volume to find N, the number of moles.
Dilutions change the concentration of solutions. When you add a solvent to a solution, it produces a solution of lower concentration.
You can find the new concentration with this equation. The molarity times the volume of the original solution equals the molarity times the volume of the diluted solution. The Mouton solution is 6 cows and a gallon of chocolate syrup. When you mix a basic solution with an acidic solution, the mixture becomes neutral. When the solution becomes neutral, it has reached the equivalence point. At the equivalence point, the number of positive hydrogen ions equals the number of negative hydroxide ions, and therefore the solution is neutral.
No, that's not a titration. A titration is yet another way to determine the concentration of a solution. All you have to do to find a concentration with a titration is add an unknown concentration to a known concentration until the mixture reaches the equivalence point.
The limiting reagent is the reactant that limits the amount of product you can get from your chemical reaction. It's the reactant you run out of first. To find the limiting reagent, first convert the amounts of your reactants from grams to moles. Then consult your balanced chemical equation to see in what ratio the reactants will react. If your reactants react in a 1-to-1 ratio, and you have less of one reactant than you have of another, the one that you have less of is the limiting reagent.
The term yield refers to the amount of product you get from a reaction. There are 3 different kinds of yields. The theoretical yield is the amount of product you predict you would get from a reaction based on its balanced equation. The actual yield is the amount of product that you actually get from an experiment.
The percent yield is the actual yield divided by the theoretical yield times 100. And that's it for review of Chem 1. Cool.
Section A, enthalpy. Enthalpy.
Before we dive into enthalpy, let's straighten out a few of the associated terms. System refers to all the substances taking part in a reaction, including the reaction vessel. Surroundings refers to the rest of the universe.
Here's an example. Let's say we have some vinegar in a beaker and we add a couple of grams of baking soda. The baking soda will react with the vinegar in the beaker, creating a stinky, bubbly mess. The beaker is part of the system because it is the reaction vessel. Everything outside the beaker is considered the surroundings. Chemists widely use Greek letters to stand for words in mathematical equations. The Greek letter delta, which to you non-Greeks looks like a triangle, it just means the change in something. As you study enthalpy, you'll see a lot of equations that have deltas in them. Just read the delta as the change in. When you see delta H in enthalpy equations, you can just read it as the change in heat.
Now, here's the scoop on enthalpy. Enthalpy is just a fancy word for the amount of heat in a system at constant pressure, the system being whatever part of the universe you've decided to study. Enthalpy considers the heat that flows out and the heat that flows into the system. In other words, the change in heat that happens as a result of a reaction. And as the guy in the toga mentioned, the change in heat, the difference between the amount of heat you started out with and the amount of heat you ended up with, is represented in the equations by the Greek letter delta. The letter H stands for heat, so delta H stands for change in heat.
When you measure the enthalpy change that occurs during a reaction, delta H is equal to the enthalpy of the products, or the stuff you end up with at the end of the reaction, minus the enthalpy of the reactants, or the stuff you started with at the beginning of the reaction. This equation represents the change in the enthalpy.
There are 2 types of reactions which involve the exchange of heat: endothermic reactions and exothermic reactions. In an endothermic reaction, heat flows into the reaction. When heat flows into a system, the change in heat, or delta H, for the reaction will be a positive number. The endo in endothermic kind of sounds like into. Endo, into. See? It makes sense that in an endothermic reaction, the change in the amount of heat is a positive number because there is a positive heat flow into the system.
When heat flows out of a system, on the other hand, it is an exothermic reaction. That's real easy to remember because exo sounds like exit. In an exothermic reaction, heat is exiting the system. When you calculate how much heat exits the system from an exothermic reaction, the number you get for delta H will be negative. That makes sense too. When heat exits the system, you have a negative heat flow. The heat is going out.
During an exothermic reaction, the heat flows from the reaction system to the surroundings. Bobo the Clown's propane stove is the reaction system, and Bobo is part of the surroundings. The propane stove is creating an exothermic reaction, and the heat from the reaction is flowing into the surrounding area, and into Bobo's weenies. In an exothermic reaction, delta H is negative.
During an endothermic reaction, there is a flow of heat from outside going into the reaction system. For example, when little Joey tied his father's shoelaces together, little Joey's dad suffered a nasty bump on his head. Dad is taking advantage of the endothermic reaction going on in the commercial ice pack. The chemical reaction in the commercial ice pack draws the heat from the warmer body, Dad's bruised and lumpy head, to the cold ice pack. So the ice pack is the reaction system, and the heat from the surroundings, in this case, Dad's head, is flowing into the reaction system. In an endothermic reaction, delta H is positive.
We're moving pretty fast here, but this information is important. So if you don't get something right away, just rewind and watch it again.
Standard enthalpy is the heat exchange during a reaction when the reactants and the products are in their standard states. A substance is in its standard state under these conditions. These are standard for all substances. The substance must be at 25 degrees Celsius, 1 atmosphere pressure, and in its most stable form. Pressure refers to the pressure exerted on the substance by the air around it, and an atmosphere, which is abbreviated ATM, is simply a unit used to measure pressure.
The standard enthalpy of formation, or delta H of formation, is the enthalpy change, or heat change, during a reaction that forms a compound from elements that are in their standard states at 25 degrees Celsius and 1 atmosphere pressure. In other words, elements in their standard states form a compound that's in its standard state, and the heat exchange that happens during the reaction is called the standard enthalpy of formation.
Now here comes some good news. You don't have to calculate enthalpies of formation. Some nice chemists did that for you. You can just look them up in a table in your chemistry textbook. Also, the standard enthalpy of formation for all elements is 0. You can plan on it. That's only true for elements like helium, oxygen, or copper. Compounds are different. You need to look up the enthalpy of formation for any compounds. So you don't need to calculate standard enthalpy of formation for elements.
At Atomic Mass University, we have an academic program renowned throughout the molecular universe. We offer courses in everything for the undergraduate particle, including stoichiometry, comparative enthalpy, orbital studies, and business administration. Plus, AMU's academic program is accredited by the law of conservation of mass, Avogadro's constant, and the first law of thermodynamics.
Okay, here's another rule for you to remember. It's called Hess's Law, and it's pretty easy. According to Hess's Law, the total enthalpy change for a reaction equals the sum of the enthalpy changes of the intermediate steps. In other words, if your total reaction consists of 3 little reactions, you add up the enthalpy changes of the 3 little reactions and get the total enthalpy change for the reaction. Just remember it, because you'll need to know it for a problem.
Using Hess's law and what we know about the standard enthalpy of formation, we can calculate the enthalpy change for a reaction with this equation. The enthalpy change of the reaction equals the sum of the standard enthalpy of formation for each of the products, or the stuff you end up with, minus the sum of the standard enthalpy of formation for each of the reactants, or the stuff you started with. Put on your toga and we'll show you how to use this Greek-looking thing.
Here's the reaction between sulfur dioxide, SO2, and oxygen to form sulfur trioxide, SO3. To find the standard enthalpy change that goes along with this reaction, first take the standard enthalpy of formation for SO3, the product, and multiply it by 2, since the 2 in front of the SO3 in the product indicates that we have 2 moles of it. This is the enthalpy of the product, the sulfur trioxide we end up with. Then subtract the sum of the enthalpies of formation of the reactants, the starting stuff. That's 2 times the standard enthalpy of formation of SO2 plus the standard enthalpy of formation of O2. Remember, the numerical values for the standard enthalpy of formation for each chemical can be found in tables in any general chemistry textbook. So don't stress about it, just look them up and plug them in. The standard enthalpy of formation for our product, sulfur trioxide, is negative 395.2 kilojoules per mole. For sulfur dioxide, it's negative 296.9 kilojoules per mole. And for oxygen, the standard enthalpy of formation is 0, because the standard enthalpy of formation of any element is always 0.
So here we substitute the values into our equation. We have 2 times negative 395.2 minus 2 times negative 296.9 plus 0. That equals negative 790.4 minus negative 593.8. Subtracting negative numbers is just like adding, so we get that the total change in enthalpy for this reaction is negative 196.6 kilojoules. Since the change in energy is negative, that means that the heat is exiting the reaction.
Heat is flowing out of the reaction. What kind of reaction is it? Exothermic, sir!
If it was positive, it would be an endothermic reaction.
So, enthalpy is the heat exchange that happens during a reaction. When heat exits the reaction is called exothermic. When heat goes into a reaction from the surroundings, it's called an endothermic reaction. The standard enthalpy of formation is the enthalpy change during a reaction that forms a compound from elements in their standard states at 25 degrees Celsius and 1 atmosphere pressure. Hess's law tells us that the total enthalpy change for a reaction is the sum of the enthalpy changes of the little reactions that make up the total reaction.
Section B, calorimetry.
Calorimetry measures the heat absorbed or created in chemical reactions.
Rock and roll, dudes!
The heat absorbed or created is determined by heat capacity and by molar heat capacity. Heat capacity is the amount of heat you need to raise the temperature of an object or substance by 1 Kelvin. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. The heat capacity of 1 gram of a substance, which is the heat required to raise the temperature by 1 Kelvin, is called specific heat. Specific heat is another thing you can just look up in your chemistry textbook. Don't you just love that?
Let's hear those again.
Heat capacity is the amount of heat required to raise the temperature of an object or substance by 1 Kelvin. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. Specific heat is the heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. You can look up specific heat in a chemistry text.
The specific heat of lead is 0.129 joules over grams times Kelvin. So that's the amount of heat required to raise 1 gram of lead by 1 Kelvin. You find this number on a specific heat chart in your book. So how many joules of heat are required to raise the temperature of 291 grams of lead from 21.9 degrees Celsius to 40.8 degrees Celsius? We'll use this new formula to find out. The quantity of heat needed equals the change in temperature times mass times specific heat. This formula, which you'll find on your insert card, lets you determine how much heat you need to add to a substance to heat it up to a specific number of degrees. This is an easy problem because we have all this information already. Some of it's in the question, and we looked up the specific heat of lead. It's 0.129 joules over grams times Kelvin. So we just need to plug in the numbers. Our change in temperature is 40.8 degrees minus 21.9 degrees, which equals 18.9 degrees. So plug that in. The mass we are dealing with is 291 grams. So plug it in. And the specific heat of lead is 0.129 joules over grams times Kelvin, which we found on the chart. So that goes in. So we have Q equals 18.9 Kelvin times 291 grams times 0.129 joules over grams times Kelvin. The amount of heat we need to raise this 291 grams of lead by 18.9 Kelvin is 709 joules.
So, calorimetry measures the amount of heat absorbed or created in reactions. Heat capacity is the amount of heat required to raise the temperature of an object or substance by 1 Kelvin. Molar heat capacity is the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. And specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 Kelvin. You can look up the specific heat of substances in your chemistry textbook.
Part 2. Atomic Structure.
Most of the stuff you've learned so far in chemistry has to do with formulas, calculations, and terms. Quantum mechanics is a little different. It's not anything you'll have to calculate or measure. It's more of a concept, a theory explained with numbers, letters, and pictures. The quantum mechanical theory helps us understand where the electrons are in atoms and molecules. Now, it's important for us to know about where the electrons are because electronic properties, like the properties that determine the shapes of the molecules, depend on where the electrons are. So pay close attention to this stuff and don't get frustrated.
Section A, Quantum Mechanics.
Quantum mechanics is a theory of the behavior of electrons in atoms and molecules. Of course, electrons are unbelievably tiny, so figuring out where they are and what they're doing at any particular moment is really hard. One problem that scientists have run across is deciding whether the electron should be considered a particle that's localized in space or a wave that's spread out in space. Scientists call this dilemma wave-particle duality. A few, like Erwin Schrödinger, dedicated their lives to studying this perplexing problem.
Schrödinger decided that the best description of electrons' behavior combines the particle and the wave ideas. And most scientists agree. He used some big ugly math as a basis to construct pictures of where the electrons might be in atoms and molecules. These theoretical representations, called orbitals, show you where the electron is 90% of the time. An electron's orbital describes 3 things about the electron. Number 1, its average distance from the nucleus of the atom. Number 2, what shape its possible path forms. This shape is called the distribution. And 3, how the distribution is oriented in space. In other words, where it is in relation to the atom's nucleus and the other orbitals.
Remember those 3 things. An electron's orbital describes 1, its average distance from the nucleus of the atom, 2, what shape its possible path forms, this shape is called the distribution, and 3, how that distribution is oriented in space, in other words, where it is in relation to the atom's nucleus and the other orbitals.
These 3 characteristics of an electron's orbital are described by 3 numbers, called quantum numbers.
Quantum numbers. Quantum numbers.
Now, these quantum numbers are a little weird, and they all relate to each other, so bear with us.
The first, or principal quantum number, is represented by a lowercase n, and it describes how far, on average, the electron is from the nucleus of the atom. The second quantum number is represented by a lowercase l, and it's called the azimuthal quantum number. It describes the shape formed by the electron distribution, or the shape of the possible path the electron can take. Finally, m sub l, the magnetic quantum numbers, describe where the orbital is in relation to the nucleus and the other orbitals. We'll now tell you more about each of these quantum numbers.
The principal quantum number, represented by a lowercase n, indicates how far an electron is, on average, from the nucleus. N can have whole number values of 1 or greater. So you'll see values like n equals 1 or n equals 2 or 3 and so on. As the value of n increases, the orbital gets bigger and the electron can range farther from the nucleus.
Think about the Earth orbiting the Sun. The Sun is like the nucleus. The distance between the revolving Earth and the Sun is like the n quantum number. N tells you how far the electron is, on average, from the nucleus.
The azimuthal quantum number, represented with a lowercase l, defines the shape of the orbital.
Straight from the Temple of Azimuthal.
Schrödinger's mathematical distribution indicates an area around the nucleus in which the electron is likely to be. That area, also called the distribution, forms a shape like a sphere shape or a dumbbell shape. We'll get to the specific shapes of the orbitals in a minute. For now, just remember that the azimuthal, or L, quantum number indicates the shape of the orbital.
The L quantum number is related to the N quantum number because L must be a value between 0 and n minus 1. So for instance, if n equals 2, then L must be 0 or 1. If n equals 3, then L can be 0, 1, or 2. And if n is 1, then L must be 0. Chemists use a letter to stand for the L quantum number. The designated letters are S, P, D, and F. So, if L equals 0, we use the letter S to represent that number. If L equals 1, we use the letter P. If L equals 2, we use the letter D, and if L equals 3, we use the letter F. These are standard. Substituting letters for the values of L makes it easy to express the N and L quantum numbers together. You can find this quantum number letter scheme on your insert card.
So for instance, if n equals 1 and L equals 0, you can refer to the orbital as a 1s orbital. If n equals 2 and L equals 1, you can call it a 2p orbital. For a 2p orbital, 2, the n quantum number, tells us how far the electron is on average from the nucleus, and p, the letter representing the L quantum number, tells us the shape of the orbital.
Say this figure skater is an electron going around the nucleus. The shape formed by her path is a lot like the L, or azimuthal quantum number, which tells you the shape of the area in which the electron is likely to be.
The magnetic quantum number, called m sub L, describes the orientation of the orbital in space. In other words, it tells you where the orbital lies in relation to the nucleus and the other orbitals.
The value of m sub L is related to the value of the L quantum number, because m sub L consists of the integers between negative L and L. So for instance, if an orbital's L quantum number is 2, m sub L is negative 2, negative 1, 0, 1, and 2. If L is 3, then m sub L is negative 3, negative 2, negative 1, 0, 1, 2, and 3. So whatever the L is, then the m sub L can have values from positive L to negative L.
I quantum number.
Shape of the orbital.
Pretend Dick's dumbbell is the orbital of an electron, and Dick's hand is the nucleus. The n quantum number will tell you the distance between Dick's hand and the ends of the dumbbell. That's how far the electron is from the nucleus most of the time. The dumbbell-shaped path is determined by the L, or azimuthal quantum number. The angle of Dick's dumbbell is like the m sub L, or magnetic quantum number. The magnetic quantum number describes the orientation of the electron's path in space.
A group of orbitals with the same principal, or n quantum number, make up what's called an electron shell. Remember, the n quantum number tells you how far an electron is, on average, from the nucleus. So a group of electrons that are cruising around at the same distance from the nucleus make up an electron shell. All the electron orbitals with a principal, or n quantum number of 1, are in the first shell. All the orbitals with n equals 2 form the second shell. All the ones with n equals 3 form the third shell, and so on, and so on, and so on, and so on.
Now let's get into the details of this quantum number thing.
Orbitals that have the same n and L values form what's called a subshell. You might have a couple of orbitals that have n equal to 2 as the principal quantum number, and L equal to 1 as the azimuthal quantum number. These orbitals will have electrons that congregate at the same distance from the nucleus, and the areas where the electrons are likely to be are the same shape. These orbitals form a subshell.
So, for instance, if there is one orbital with the quantum numbers n equal to 1 and L equal to 0, we say this orbital makes up the 1s subshell. Remember, the letter S in 1s stands for the L value, which in this case is 0. Here's another example. All orbitals with the quantum numbers n equal to 2 and L equal to 1 we call the 2p orbitals, and we say they are in the 2p subshell.
Now we're ready for pictures. No, pictures of orbitals.
So the three quantum numbers describe the orbitals they represent. An orbital with the quantum numbers n equals 1, L equals 0, and m sub L equals 0 is a 1s orbital. S orbitals are sphere-shaped. This diagram shows the shape of a 1s orbital, and the dots indicate the distribution, or the range in which the electron may travel. The area where the dots are the most dense is where the electron in this orbital is statistically most likely to be. The intersection of the axes corresponds to the nucleus of the hypothetical atom we're representing.
S orbitals are sphere-shaped.
Here's a picture of a 2s orbital. Notice the probable distance that the electron can range from the nucleus is larger than in the 1s orbital. This makes sense since the 2 indicates that the principal quantum number is bigger, and therefore the electron orbits farther from the nucleus. The areas where the dots are denser are the areas where the electron is more likely to be. This is where I hang out.
The blank space is an area where, according to the math that backs up this theory, the electron probably won't hang out.
You won't catch me here.
That blank space is called a node.
The 3s orbital is larger yet, and it has 2 nodes.
P orbitals are dumbbell-shaped.
P orbitals?
Yeah. They are dumbbell-shaped because the electron distribution is separated at the nucleus by one of those nodes we just talked about. So the electron in a p orbital hangs out on one side of the nucleus or the other. There are 3 of each of the p orbitals. 3 2p orbitals, 3 3p orbitals, 3 4p orbitals, and so on. And to make it easy to tell the 3 of each apart, we label them with the subscripts x, y, and z to indicate which axis the orbital is lined up with.
But there's an important thing to remember about the subscripts. They don't necessarily have any relation to the m sub L quantum number, which officially indicates the orientation of the orbital in space. In more advanced chemistry classes, you'll learn why the subscripts and the m sub L quantum number don't necessarily correspond. But in this introductory material, you'll just have to take our word for it. That said, back to the orbitals. Like with the s orbitals, the p orbitals get bigger as the value of n increases. Remember, the number 2 in 2p is the n quantum number. The bigger n is, the further away from the nucleus the electron hangs out. So, the 4p electrons are, on average, further from the nucleus than the 2p electrons. All 3 of the 2p orbitals are the same size, but they differ from each other in orientation. In other words, they're arranged differently in space around the nucleus. It works the same way for the 3p orbitals. All 3 of the 3p orbitals are the same size, but they are arranged differently around the nucleus.
In the third electron shell and beyond, when n, the number that indicates the average distance from the nucleus, equals 3 or more, we can have d orbitals. There are different types of d orbitals. So for the 3d orbital, there are 5 types. 5 3d orbitals, 5 4d orbitals, 5 5d orbitals, and so forth. We use subscripts for the 5 different orbitals so we can keep them straight, like we did with the p orbitals. But again, remember that the subscripts do not always correspond with the m sub L quantum numbers. Also, just like with the p orbitals, the d orbitals look alike but are oriented differently, except for one conspicuous oddball. There is one d orbital that looks like a donut. It looks different, but has the same energy as the other d orbitals. Remember that when we talk about 3d orbitals, we are referring to an orbital with a principal, or n, quantum number of 3, and an azimuthal, or L, quantum number of 2, which is represented by the letter d. 4d orbitals have the principal quantum number 4, which means they are bigger than the 3ds, but have the same azimuthal quantum number as the 3ds, so they have the same shape.
The f orbitals are too complex to represent on your two-dimensional TV screen. As a matter of fact, your textbook probably doesn't even give you pictures of f orbitals because your book is only 2 dimensions just like your TV. But don't sweat it, because
At this stage of your chemistry career, you don't need to worry about what the f orbitals look like. Just know that they're there.
This diagram of the periodic table shows the order in which the elements fill their atomic orbitals, starting at the top and reading each line across from left to right. The electrons fill more orbitals. You see hydrogen and helium at the top labeled 1s because they only need the 1s orbital to contain their electrons. Lithium and beryllium are labeled 2s because with 3 and 4 electrons respectively, they need the 2s orbital to hold them. Boron, with its 5 electrons, needs one of the 2p orbitals. The next higher energy orbital is the 3s orbital, and sodium and magnesium with 11 and 12 electrons respectively use that orbital. The next available orbital is the 3p orbital, then the 4s orbital, and so on all the way through the 5f orbital at the bottom of the table.
There are a few more things you should know about orbitals. Each orbital can hold a maximum of 2 electrons. There is an order to filling the orbitals. We'll go into detail on that now. An element's electrons will fill the lowest energy orbital, the 1s orbital, which is nearest the nucleus first. So hydrogen puts its single electron in the 1s orbital. Helium has 2 electrons, so it fills its 1s orbital. Lithium, with 3 electrons, fills its 1s orbital and sends its third electron to the 2s orbital. Boron has 5 electrons, so it fills the 1s and 2s orbitals with 2 electrons each, then sends its 5th electron to the 2p orbital. This pattern continues for all the elements. The elements with more electrons fill more orbitals. You can look once again to the periodic table to tell you the order in which the elements fill their atomic orbitals.
Orbital spins!
Wolfgang Pauli is the guy who... Wolfgang Pauli! He's the guy who figured out that an orbital can only hold 2 electrons. He also proposed that the 2 electrons in the orbital must have opposite spins. This is called the Pauli exclusion principle.
Hey guys, come here! What do you say we talk about something really interesting? 2p orbitals!
Come on, guys. Let me talk. I want to be a part of this. This is fun.
No, Wolfgang! You're excluded!
You guys just wait. Someday I'll be famous. According to the exclusion principle, named after me, Wolfgang Pauli, each orbital can only hold 2 electrons, and they must have opposite spins.
Take helium as an example. Helium has 2 electrons filling its 1s orbital. One of the electrons in the 1s orbital has what chemists call a positive spin, and the other has a negative spin. When 2 electrons with opposite spins fill an orbital together, we say those electrons are paired.
I do.
I do.
If an orbital has only 1 electron, we call it an unpaired electron.
So lithium, with its 3 electrons, has paired electrons in its 1s orbital and 1 unpaired electron in its 2s orbital. Lithium's paired electrons have opposite spins, 1 positive and 1 negative.
Section B, writing electron configurations.
Orbital diagrams represent electron configurations, or the way electrons are distributed among the atom's orbitals using boxes and half arrows. Now that you know how orbitals fill in order of increasing energy with 2 electrons per orbital, understanding these diagrams will be a piece of cake for you.
Let's start with hydrogen again. The orbital diagram for hydrogen uses just 1 box labeled 1s with a half arrow pointing up. The half arrow represents hydrogen's 1 electron, which occupies the 1s, or lowest energy orbital. The notation 1s1 also represents hydrogen's electron configuration. 1s is the orbital hydrogen uses, and the superscript 1 tells us that hydrogen has 1 electron in that orbital.
Next, there's helium. Its 2 electrons are both in the 1s orbital. So, its orbital diagram also uses only 1 box, but helium's 1s box has 2 half arrows, representing its 2 electrons. Notice that the half arrows are pointing in opposite directions, showing the opposite spins of the 2 electrons in the orbital. The notation 1s2 tells us that helium fills the 1s orbital with 2 electrons.
1s2 means there are 2 electrons in the 1s orbital.
Lithium, with its 3 electrons, needs 2 boxes for its orbital diagram. The 1s box is filled with a pair of electrons, and lithium's 3rd electron, the unpaired electron, goes to the 2s box. We describe lithium's electrons with this notation: 1s2, 2s1. Lithium fills the 1s orbital with 2 electrons and uses the 2s orbital for its unpaired electron. Now let's skip to boron, which has 5 electrons.
Boron has paired electrons filling its 1s and 2s orbitals, and its 5th electron goes unpaired to one of the 2p orbitals. So boron's notation is 1s2, 2s2, 2p1.
Next, jump down to sodium with its 11 electrons. Sodium fills the 1s, 2s, and 2p orbitals and sends its 11th electron to the 3s orbital because the 2p orbital is full. Sodium's notation is pretty lengthy since it uses a lot of orbitals. It's 1s2, 2s2, 2p6, 3s1. Even without looking at the orbital diagrams, the notation alone tells us that sodium fills the 1s orbital, the 2s orbital, all 3 of the 2p orbitals, and sends its unpaired electron to the 3s orbital.
When atoms lose or gain electrons, they acquire a charge and become ions. The orbital diagrams for the ions reflect the addition or subtraction of the electron. For instance, here's the orbital diagram for the neutral element sodium again, and here's the orbital diagram for the positive sodium ion. The positive sodium ion has lost an electron, so its configuration is 1s2, 2s2, 2p6. When an atom loses an electron, it will always lose the electron from its outermost orbital. In the case of the neutral sodium, it lost the electron in the 3s orbital when it became an ion, because the 3s orbital is the outermost energy orbital that sodium was using.
So, orbitals are just pictures of where the electrons are and what they're doing in an atom. Electrons will fill orbitals in a fixed pattern, starting with the lower energy orbitals closest to the nucleus, then moving up and out from there. And by now, you're probably wondering, who the heck cares where the stupid electrons are? Well, aside from the fact that you'll be tested on it, you need to know where the electrons are in an atom because the positions of the electrons affect how the atoms come together, or bond, to form molecules.
Part 3, Chemical Bonding. Section A, Lewis Structures.
Hi, I'm the American chemist, Gilbert Lewis. Well, not really, I'm actually just a representation of Gilbert Lewis. And this is a chlorine molecule. Well, not really, it's actually a representation of a chlorine molecule. The representation is called Lewis structure, named for Gilbert Lewis. The real Gilbert Lewis developed this method of representing the covalent bonds in real molecules. Lewis structures, also called electron dot structures, use dots to show the number of electrons in the outer shell, known as the valence shell, of an atom. Lewis structures indicate the bonding pattern between the atoms that form a compound. And this is my pet frog, George. Well, actually, George isn't a real frog. He's just a representation of a real frog. When we draw the Lewis structure of an atom, we have to consider the octet rule. According to the octet rule, when a compound forms, an atom gains or loses electrons or shares pairs of electrons until it has 8 electrons in its valence shell. So the atom will keep sharing till it has 8 electrons in its outer shell. Valence is just a fancy way of saying outer. An atom with 8 electrons in its valence shell is a happy atom.
Valence means outer.
Here's one way the atoms sodium and chlorine become happy atoms. As sodium and chlorine mix, the chlorine atom removes one of the electrons from the sodium atom, leaving the sodium with a positive charge and a filled valence shell. The chlorine atom now has a negative charge and a filled valence shell. Now they're happy!
When you draw the Lewis structures of simple molecules, you don't have to worry about other ways of drawing the structure because there's probably only one way to draw it. There may be a few ways, however, to draw Lewis structures for more complex and beastly conglomerations.
Sometimes a single Lewis structure cannot, by itself, describe the electrons in a molecule. In some cases, there are several versions of the Lewis structure for a molecule or ion which are all correct. These varying but correct ways of representing an atom or molecule are called resonance structures.
These resonance structures are all valid representations of the nitrate ion. Notice that the only difference between these ions is the placement of the electrons forming the bonds. In each ion, there is a central nitrogen atom and 3 oxygen atoms. Each ion has one double bond, but the double bond occurs between the nitrogen and a different oxygen atom in each case. Other than the placement of the double bond, everything else about the ions is the same. The numbers and types of atoms are the same, and the atoms themselves are arranged the same way. The only difference between the 3 ions is the placement of the double bond. Since the nitrate ion can form with a double bond in any of these 3 locations, we must draw the Lewis structures for all 3 possibilities. These 3 accurate possibilities are called resonance structures. Remember that according to the octet rule, when a compound forms, its component atoms will gain, lose, or share electrons until they have 8 electrons in their outer shells. An atom with 8 electrons in its outer shell is a happy atom.
Unfortunately, there are a few exceptions to the octet rule. The obvious exception is hydrogen.
Hydrogen has a filled shell when it has 2 electrons surrounding it. So when it gets to 2, it's done. No more filling. That's it. So there is no room for 8 electrons in hydrogen's outer shell. Another example is boron trifluoride, BF3, where boron has 3 electrons in its valence shell, and fluorine has 7 electrons in its valence shell. 3 fluorine atoms bind to the boron atom. The molecule is complete, although boron only has 6 electrons in its outer shell. Boron is referred to as an electron-deficient element.
Section B, atomic bonding.
We'll talk about 2 kinds of bonds that form between atoms, ionic bonds and covalent bonds. Now here's Einsteinium, the genius element, to tell you about ions.
The elements have the ability to form ions. Ions are like atoms, except ions have an electrical charge and atoms are neutral. Then an electron, which you remember has a negative charge, is removed from an atom. You get a positive ion. When an electron is added to an atom, we have a negative ion.
Let us clarify that for you. Electron removed, positive ion. Electron gained, negative ion. Like if you have a cavity removed, you feel positive. If you gain a cavity, you feel negative.
Removed.
Positive.
Gained.
Negative.
Ionic bonds are the bonds that form between oppositely charged ions. They are basically just what we think of as magnetic.
Ionic bonds form when ions gain or lose an electron as they try to fill their valence shell with 8 electrons. All ions and atoms want 8 electrons in their valence shell.
Hey, what the heck is this thing?
I don't know.
Weird.
Our earlier example of the reaction between sodium and chlorine to form sodium chloride illustrates ionic bonding. The chlorine removes an electron from the sodium, making the 2 atoms into oppositely charged ions. The ions are attracted to each other and to the other ions which form the sodium chloride crystal.
So the charge of an ion depends on how many electrons it has gained or lost in its valence shell. Just like atoms, an ion looking to fill its valence shell will easily combine with another ion or atom that also needs to fill its valence shell. The 2 ions can share electrons. The shared electrons allow the ions to become happy atoms with full valence shells. When ions combine so they can share electrons, the bond that forms between them is called a covalent bond.
So you get a covalent bond when two atoms share an electron. Covalent bonds usually form between nonmetallic elements. Water, oxygen, and hydrogen molecules are examples of molecules with atoms that share electrons through covalent bonds.
Here at Atomic Mass University, we have a diverse student population which comprises the entire range of the periodic table, from hydrogen to lawrencium. And at AMU, these students enjoy a rich social life of chemical interaction. Some students assemble themselves into compounds, while others prefer to hang out with their own element. AMU students bond easily as friends, and sometimes they form strong covalent bonds.
The Lewis structure for fluorine illustrates a single covalent bond. Notice that one pair of electrons is shared between two fluorine atoms. Oxygen atoms share two pairs of electrons, forming a double covalent bond. And nitrogen atoms share three pairs of electrons. That's 6 electrons shared between two nitrogen atoms in the molecule, forming a triple covalent bond.
Two atoms with different electronegativities that bind together form a polar covalent bond. We'll explain.
Electronegativity is the ability of an atom in a molecule to attract the electrons of a covalent bond closer to itself. Some atoms are more electronegative than others, meaning that in their covalent bonds with other atoms, they pull the shared electrons closer to themselves and a little farther away from the atoms they are bonding with.
Kind of like the IRS, they take more of something than they can give.
When two atoms with different electronegativities bond, it's called polar covalent bonding. Polar covalent bonds are still covalent bonds, just a different version. Since the atom with greater electronegativity pulls the negatively charged electrons away from the atom it's bonded with, that pulling atom assumes a slight negative charge. You see, it's pulling the negatively charged particles, or electrons, closer to itself, so it's getting more negative. The other atom, with its electrons pulled away from it, assumes a weak positive charge because the negative electrons in the covalent bond are being pulled away from it a bit.
Let's take water again as an example. The oxygen atom of the water molecule has a greater electronegativity than the hydrogen atoms. As a result, the electrons of the covalent bond between the oxygen and the hydrogen are drawn closer to the oxygen atom, creating a slight negative charge on the oxygen atom and a slight positive charge on the hydrogen atom.
Electronegativity decreases as you go down a column in the periodic chart and increases as you go to the right across a row of the periodic chart.
Listen, every time we get together, you start hogging all the electrons.
I know. It's my electronegativity. I just can't help it.
So, there are ionic bonds and covalent bonds and James bonds. But that's not important right now, is it? Chemistry is important. Ionic bonds form between two oppositely charged ions, and covalent bonds form when two atoms share an electron. Strong electronegative atoms pull the shared electrons in a covalent bond toward themselves, causing the molecule to become polar. Polar molecules have a slight positive charge on the less electronegative atom, and a slight negative charge on the more electronegative atom. And that is bonding.
Section C, bond energy. Bond energy, represented by the letters BE, refers to the energy needed to break or form bonds. A whole mole's worth of bonds, as a matter of fact.
Yes, we're back to the mole.
Say you have 1 mole of gaseous molecules, and the molecules are diatomic, which means that each of the molecules consists of 2 atoms. The bond energy is the amount of energy needed to break up 1 mole of the molecules into single atoms. So if you break 1 mole of diatomic molecules into 2 moles of atoms, the amount of energy it takes to do that is bond energy. Conversely, if the 2 moles of atoms bond to form 1 mole of diatomic molecules, the amount of energy released when the bonds form is also called bond energy. The stronger the bonds in a molecule, the more energy is needed to decompose the molecule into its atoms. As the number of bonds between two atoms increases, the bond energy also increases. That makes sense, right? More bonds, more bond energy. And here's the best part. Bond energy is another one of those cool things you can just look up in your textbook.
Oh, thank merciful heavens.
You can use bond energy to estimate how much heat will be gained or lost during a reaction. The heat gained or lost during a reaction is the reaction enthalpy.
So, to use bond energy to find the reaction enthalpy, you just add the bond energies of the bonds broken during the reaction, and from this value, you subtract the sum of the bond energies of the bonds that were formed.
Reaction enthalpy.
Here's what it looks like. This diagram shows the bonds in the following reaction. Chlorine gas plus methane gas make chloromethane gas plus hydrogen chloride. So in this reaction, one chlorine-chlorine bond breaks, and one hydrogen-carbon bond breaks. One chlorine-carbon bond forms, and one hydrogen-chlorine bond forms.
The reaction enthalpy, delta E, equals the sum of the bond energies of the bonds broken minus the sum of the bond energies of the bonds formed. In our case, delta E equals the sum of the energies of the bonds that break between a chlorine and a carbon and between a hydrogen and a carbon, minus the sum of the energies of bonds that are formed between a chlorine and a carbon and a hydrogen and a chlorine.
So find in your textbook the bond energy that's given off when two chlorine atoms break apart. That's 242 kilojoules. And add the energy given off when you break the bond between hydrogen and carbon, 413 kilojoules. And from that sum, subtract the sum of the energy given off when carbon and chlorine break apart, 328 kilojoules, plus the energy given off when hydrogen and chlorine break apart, 431 kilojoules. Gives us 655 kilojoules minus 759 kilojoules. The enthalpy of this reaction is negative 104 kilojoules.
So, bond energy is the energy needed to break or form bonds. You can look up bond energies in your book and use those values to calculate how much heat will be gained or lost in a reaction.
So, in this tape you learned lots of awesome chem stuff, like enthalpy
and calorimetry,
quantum mechanics and electron configurations,
and Lewis structures and more.
Feel free to give us a call at Cerebellum at any time for any reason, especially if you need a good eye wash, at 1-800-238-9669. We'd love to hear from you.